All right, so we said next week on, let's try Monday. It's the same for you, right? So how about Monday next week from 3:15 to 4:15? Is everybody okay with attending from 3:15? Or you have other classes?
I come in halfway through.
Do you have a class before?
I was trying to be rude there.
Okay, so earlier than that, it would have to be early in the morning. I'll have to compose a message then with my possible times. It will be recorded anyways, but,
Yes, that works.
but I would rather, you be able to attend. Okay, so I'll make a list and then we'll see what happens. Okay, so we are in 6.1. We talked about inner product spaces already. Just to remind you, that is a vector space together with an inner product on V. An inner product being a function that assigns to every ordered pair of two vectors, x comma y, a scalar in F with certain properties, right? The association has to be linear in the first variable. If you decide to switch order between the two entries, you can do that by putting the conjugate on top. And the inner product between a vector and itself is always positive unless the vector is the zero vector. So now the last part of this section is the notion of orthogonal and orthonormal sets in an inner product space. So first of all, two vectors x and y, the two vectors are called orthogonal, provided that their inner product is zero. Then if you have a set of vectors, then you're going to say that the entire set is orthogonal if any two vectors in the set are orthogonal. And furthermore, a vector is a unit vector if its norm is 1, but furthermore, a set is called orthonormal if it is orthogonal, containing unit vectors only. Let's look into this a bit. Rn, let's say. Together with that standard inner product, well, actually, let's do Fn. The standard inner product being this. So X is an n-tuple with entries x1 through xn. Y is an n-tuple with entries y1 through yn. The inner product between x and y was defined to be the sum of xy, yy conjugate. And let's look at the following set. That was the standard basis, right, of Fn 1, 0, 0, 0, 1, 0, and so on. The claim is that this set is orthonormal. Okay, so what does that mean? Well, first of all, it must be an orthogonal set. Orthogonal means that if you take, so S is orthogonal first. So orthogonal means that if you take any two vectors in that set, E K, let's say, and E L, then their inner product is 0. Okay, so this should hold for any K and L between 1 and n. Of course, I'm not taking the same vector twice, so I need them to be different. K and L not equal to each other.
Do all the vectors are orthogonal to each other?
Yeah, so for a set to be orthogonal, any two non-identical vectors in the set must be orthogonal to each other. So let's see. So what does the inner product between EK and EL mean? According to the definition above, this one here, for the inner product, I have to take the sum, right, of xi, yy conjugate, so what happens inside that sum? EK, imagine how it is 0, 0, 1 in position K, 0 everywhere else. EL has a 1 in position L. So when I start making that sum is 0 times 0 plus 0 times 0 up to position K, let's say K is less than L, but that's still 1 times 0 because K and L are not equal. And then 0 times 1 all the way to the end, so it will automatically be 0. So any two such vectors are orthogonal. Okay, but to be orthonormal, it must satisfy an additional thing. That is, every vector in there should be a unit vector. So for that, we need to compute the norm of every vector. So take one of those vectors like EK. Let's find its norm. Remember that the norm is defined in such a way that the norm of a vector squared is the inner product between the vector and itself, right? That is the definition of the norm based on an inner product. So what happens when I do EK inner product with EK? Right, it's the sum of 0 times 0 plus 0 times 0 up to position K when I get 1 times 1, and then everywhere else is 0 again, so I'm going to end up with 1, right? So every vector has norm 1. So they are all what is called unit vectors. So we're done, right? This is an example of an orthonormal set. Let's see, one more. Let's look at matrices 2 by 2. Matrices 2 by 2 with a Frobenius, right? Inner product. The Frobenius was inner product between A and B is the trace of B star A. Well, we're over R, so B star is in fact B transpose, right? And let's take this set containing these two matrices. And let's check if this is orthogonal or orthonormal. So what do I have to do to check that it's orthogonal? Well, there are only two vectors in there, right? So it's not that bad. The only thing that I have to check is, let me call this first one A, the second matrix B. So all I need to do is to look at the inner product between those two matrices, A and B. Which by definition is the trace of B star A, but we're over R, so the trace of B transpose A. Okay, what is B transpose A? This is B transpose times A turns into this. Yeah, and its trace is 2, right? In conclusion, the two matrices are not orthogonal, so my set is not orthonormal. It's not orthogonal. If it's not orthogonal, it has no chance of being orthonormal, because orthonormal means orthogonal plus something else, right? Now, of course, I just picked those two matrices completely arbitrary, but what I wanted to tell you is that it's very easy to get sets that are not orthogonal and not orthonormal. So it's a very special property, right, to be orthogonal or orthonormal. Okay, now let's say you have such a set. Why is it so special, or why is it so helpful to deal with orthogonal or orthonormal sets? Well, now to answer this question, we'll move to the next section. All right, so first of all, we'll extend this notion a bit. Up to orthonormal basis from an orthonormal set. So we're going to say that a basis is an orthonormal basis. If it is a basis, of course, that is also orthonormal as a set. Okay. So, for example, we've already seen one. Fn together with that standard basis. We've seen that this is an orthonormal set, right? Therefore, this forms an orthonormal basis. Okay, so we go back to that question. So why is it so nice to deal with an orthonormal set or an orthonormal basis? Well, remember that if you have a basis beta, then every vector in the space can be written as some linear combination of the vectors in the basis. How do you write that? Well, I don't know. You have to come up with that entire system of linear equations, right, and solve that thing, and it takes a while to figure this out. However, if the basis, or if your set that you're dealing with is orthogonal, then things are much easier. And here it is. You have a very nice formula for figuring out the coefficients, right, of writing that vector in that basis. Let's look into this. We're not assuming that this S is a basis, so we just take an inner product space V, and S is an orthogonal set. And then you just take a vector Y in the span of S. Of course, this extends to the idea of S being a basis. The span would be the entire space. But, okay. So, let's see why it is like this. So, if Y is an element in the span of S, that means it is a linear combination, right, of the vectors in S. There are k of them. So Y is the sum I equals 1 to k ai vi. So what we have to show is that each ai is in fact equal to this coefficient that shows in the formula here. Okay. How do we get there? So you just take the inner product between Y and the vector Vj in the set. What happens if you do this? Well, Y is the sum of ai vi and then inner product with Vj. Remember that the inner product behaves very nicely with respect to the first component there is linear, so you can just distribute this sum and take the coefficients out. So this is the sum I equals 1 to k of ai inner product between vi and vj. Now what is the inner product between vi and vj? Zero, unless, remember that j was arbitrary, unless j is exactly I, right? In that case, well, in that case, I don't know what it is because the set is not supposed to be orthonormal. It's just orthogonal, right? It's not assumed to be orthonormal. So it just turns into something like, so if j equals I, we just end up with aj norm of vj squared. So here it is. We started with this inner product. We ended up with this. So that coefficient that we're trying to find, aj, is y vj inner product all over the norm of vj squared. And that's exactly what we needed. Now, you might wonder why I can divide by the norm of Vj squared. Could that thing be 0, right? If it's 0, then it doesn't make any sense. Well, it turns out that it has no chance of being 0, and we're going to see that an orthogonal set must necessarily be linearly independent. If it's linearly independent, it cannot contain the 0 vector, right? So there's no... okay, so the set was just orthogonal. If S was orthonormal in the theorem above, then things are even nicer. Why are they nicer? Because in an orthonormal set, the norm of every VI would be 1, right? They are all unit vectors. So the formula looks even better. It is the sum, I equals 1 to k, inner product between y and vi times vi. That norm disappears. Two, let's say that thing that I mentioned before, if S is orthogonal, then S must be linearly independent. Let's prove this. So S was a collection of k vectors. Now let's just assume that some linear combination of those vectors equals 0. We want to show that all the coefficients must be 0. Okay, so what we'll do is in this equation here, in the linear combination equal to 0, we'll just take both left and right, the inner product with some Vj, fixed j. So A1 V1 plus AK Vk, inner product with Vj, equals 0, inner product with Vj, inner product between 0 and anything being 0. On the left, though, what happens, again, we have a linear combination in the first entry of the inner product. It spreads out nicely. So it's the sum, I equals 1 to k, AI, inner product between Vi and Vj. Right side was 0. But we've seen that before, right? It was an orthogonal set. Inner product between Vi and Vj is always 0 unless I equals j. So when I equals j, we get Aj, inner product between Vj and Vj, which is Aj norm of Vj squared equals 0. Okay. And I think I'm going to retrace everything back and reformulate what I want to say. So, go back and say that it's an orthogonal set containing non-zero vectors. Why should I assume this? Because and the same in the theorem above, actually. Oh, but this is given anyways, to be non-zero vectors. But why should I assume that? Well, an orthogonal set could still be orthogonal even if you throw in the 0 vector there, because the 0 vector inner product with anything you want is still the 0 vector, right? So you're not losing orthogonality if you throw in the 0 vector, but it's less interesting, let's say, from the perspective of talking about orthogonal and orthonormal basis. So If it doesn't contain 0 vectors, then it automatically must be linearly independent. Okay. So, the next question is the following. Given a finite dimensional, let's say, vector space, which is an inner product space, can we always find an orthogonal basis or orthonormal basis, right? We know that any finite vector space has a basis. We proved this before. But can we actually get an orthogonal basis? Why do I want an orthogonal basis? Well, because of this. Because it's very nice to represent things in orthogonal basis. And then once I have it orthogonal, I might even want to make it orthonormal, but that will be the easy thing. And the answer will be yes. And it's this messy thing called the Gram-Schmidt orthogonalization process. And that's exactly what it says. It says that if you have an inner product space and you have a linearly independent subset, you usually just start with a basis of V, so it's automatically linearly independent. So S was linearly independent. Then you can define another set based on the original S. You call it S prime, where the vectors are defined according to this ugly formula there. This S prime turns out to be an orthogonal set with the same span as the original set S. So imagine what I need this for. If I start with a set S that is a basis, it's already linearly independent, right, which is the first assumption here. Then from S I get to S prime, which is an orthogonal set with the same span. The span of the original set was the entire space because it was a basis. So I get a new basis that is orthogonal. We'll reformulate this at the end. I'm not going to go into the proof. It's just induction and computational. So let's just worry about how it works. So this is example 2A in the book, in this section. It says a linearly independent set is given. Apply Gram-Schmidt to obtain an orthogonal basis. And then from that, get an orthonormal basis. For the given inner product space. And the given is R3. In this question is R3 with a standard inner product on Fn in general. And the set is 101, 011, and 133. So this would be this set S that we start with. Let's just accept that it is linearly independent. So it is a set of vectors W1, W2, W3. It's not an orthogonal set because, for instance, if you take the inner product between W1 and W2, what do you get? You get 1 times 0 plus 0 times 1 plus 1 times 1. You get 1. So they are not orthogonal. It's non-trivial, I mean, the application of Gram-Schmidt. All right, so we want to construct this set. And again, more than that, this S is, in fact, a set containing 3 independent vectors in R3, so they form a basis, right? It is a basis for R3. All right, so we want to turn this into orthogonal set S prime containing vectors V1, V2, and V3. The simplest one to get is the very first one. It's here. You just start with the first vector in your set. So V1 is the vector 1, 0, 1. Let's find V2. Well, we're going to use this formula on the very top of the page, number 1, for k equal to 2, right? So V2 equals W2 minus the sum j equals 1 to, well, k was 2, so it's just 1 to 1. Inner product between WK, k is 2. So W2 with Vj divided by the norm of Vj squared. Those are all numbers so far, right, in that fraction. And this number is multiplied, I mean scalars. This number is multiplied by Vj. But again, j is only equal to 1. There is no real sum to talk about. So let's rewrite this. So it's W2 minus inner product between W2 and V1 over the norm of V1 squared times V1. Okay, so let's see what this is. W2 is the vector 0, 1, 1. What is the inner product between W2 and V1? V1 is W1, right? The inner product is the standard inner product on Fn is the sum of xi, y conjugate. So W2 with V1 is just W2 with W1, right? So 1 times 0 plus 0 times 1 plus 1 times 1. So it's 1. The norm of V1 squared is the inner product between V1 and V1. So 1 plus 1, so 2 squared. 2. And times, so 1/2 times V1, which V1 is 101. So now I get 0 minus 1/2, 1 minus 0, and 1 minus 1/2. So V2 is negative 1/2, 1, 1/2. Okay, move on. V3. V3 is W3 minus the sum. Now k is 3, so the sum went from 1 to k minus 1, right? So it's the sum from 1 to 2 of W3 with Vj. Inner product all over the norm of Vj squared times Vj. There are two of them now. W3 minus inner product between W3 and V1. Norm of V1 squared, all times V1, minus inner product between W3 and V2 over the norm of V2 squared times V2. So you can imagine what happens if you keep on going, right? If your set contained more than 3 vectors, it would be a lot of computations. All right, so W3, what's that? W3 is 1, 3, 3. Minus inner product between W3 and V1. 4. V1 is W1, so inner product between W1 and W3 is 4. Norm of V1 squared, we computed that already, it was 2. and times V1, 101. Now V2 was this one here that we computed above. This was V2. So we need the inner product between W3 and V2. So negative negative 1/2 plus 3 right? I'm doing 133 with this one, with V2. Negative 1/2 plus 3/3. So it is 4. So 4 over, let's see, what's the norm of V2 squared? Inner product between V2 and itself, 1 over 4 plus 1 plus 1 over 4, right? So 1/2 plus 1, 3/2. And V2 is all this. All right, so now let's see what happens. So this thing is just 202, right? And this is 8/3 times all that. Negative 4/3, 8/3, 4/3. So we have 1 minus 2, negative 1, plus 4/3, right? So 1/3. 3 minus 0 is 3, minus 8 over 3 is 1/3. 3 minus 2 is 1, minus 4/3, negative 1/3. This was V3, right? If I didn't make any mistake, nobody said anything, so I'll just take it for being correct. It might not be, but okay. So we found, we applied Gram-Schmidt, and we obtained an orthogonal set S prime containing 3 independent vectors in R3, so they form a basis, right? So S prime is indeed an orthogonal basis of R3. How do we get an orthonormal basis then, based on that? Well, to be orthonormal, it has to be orthogonal, so I'm going to build from S prime on, right? That was orthogonal, but it has that additional thing that every vector must be a unit vector, and clearly those vectors are not unit vectors because we got norms of 3/2 and 2, right? So how do I turn vectors into unit vectors?
Order of magnitude.
Pretty simple, right? Divide each vector by its magnitude. When you divide a vector by a scalar or multiply a vector by a scalar, you're not losing the orthogonality, right? Because the scalars, you can just move them out of the inner product. Nothing changes there. All right, so to get an orthonormal basis, I'm going to take every vector in S prime and divide it by its norm. So the first vector was V1, which is 101. We said that the norm squared of V1 was 2. So the norm is 1 over the square root. The norm is the square root of 2. So I'm going to take the vector 101 and multiply it by 1 over the square root of 2, or 1 over its norm. V2, which was this one. We said that the norm of V2 squared, right, it was here. The norm of V2 squared was 3/2. So the norm of V2 is the square root of 3/2, so I'm going to multiply it by the square root of 2/3, right? I'm going to divide by the square root of 3/2. And finally, V3 yeah. The norm of V2 is square root of 3/2. So when I divide by the norm of V2, I multiply by the square root of 2/3. Right, what norm does this last one have? So 1/9 plus 1/9 plus 1/9 is 3/9, so 1/3 square root. So 1 over the square root of 3 is the norm, right? So I'm going to multiply by the square root of 3. Okay, so we started with a basis for R3, this one here, this set S, and we turned it into an orthonormal basis for R3. Not a nice orthonormal basis by any means, right? We have a very nice orthonormal basis in R3. It's just E1, E2, E3, right? All clear and simple. However, for things that we'll see further in this section, we're going to need to actually be able to apply this procedure, starting with that given set to turn it into an orthonormal set in order to make things work. So we'll have to go through this. Okay. So as I said before, any finite dimensional inner product space must have an orthonormal basis. And if beta would be orthonormal, then you have this way of writing a vector, which we've seen before, right? We've seen at the beginning, every vector is the sum. It was x inner product with vi divided by the norm of vi squared, which is 1 if it's orthonormal, right? So this we've seen before. So the main thing is this, that every finite dimensional inner product space has an orthonormal basis. Okay, so being a finite dimensional inner product, being a finite dimensional vector space, first of all, we've seen before that it must have some kind of basis. Let's keep some order on it, so ordered basis. All right, so in particular, this beta is linearly independent. Now, Gram-Schmidt says that if you have a linearly independent set, you can find another set that is orthogonal and has the same span as the original one. Beta prime orthogonal set with span of beta prime same as span of beta. All right, but what is the span of beta? Beta was a basis, right? So the span of beta is the entire space. Okay, but then beta prime is orthogonal and generating. Being orthogonal, it means it's linearly independent, right? So it's linearly independent and generating, so it forms a basis for V, which is an orthogonal basis. Okay, but now if I have an orthogonal basis, to find an orthonormal basis, I just divide each vector by its norm. All right, and again, as I said, if you have an orthonormal basis, it's very easy to express every vector in V as a linear combination of the vectors in the orthonormal basis. Just by doing this, every coefficient is the inner product between x and Vi. Now, one immediate application of this is into the matrix associated to a linear transformation. Because the entries of that matrix, of the matrix of T in a basis beta, were given by the coefficients of the linear combination. So it must be the case that if you have an orthonormal basis, it's very easy to also compute that matrix based on the inner product. And that's exactly what happens. So corollary. So V, let V be a finite dimensional inner product space. Therefore, it must have an orthonormal basis. Let's say beta is such a thing. Let's say T is a linear operator, so a linear transformation from V to V. And let's call A the matrix of T in the basis beta. Let me not call it corollary because I'm not going to make like a statement and then prove it. Just say note. Okay, so now how did we find the entries of the matrix A? Well, if beta would be, let's say, V1 through Vn. To find the entries of the matrix A, we just did T of Vj. And we said that if T of Vj could be expressed like this, the sum is, it must be some linear combination of vectors V1 through Vn. It's a linear combination that looks like this, the sum of Aij Vi, right? And then Aij would be the entries of the matrix A. However, according to this theorem above, with x replaced by T of Vj, what do I get? I get that T of Vj is the sum of the inner product between T of Vj and Vi times Vi, right? Just replace x by T of Vj. But every vector, when written as a linear combination of the elements of a basis, that linear combination is unique, right? There is no way to write a vector in two ways as linear combinations of the vectors in a basis. We've seen that before. So here, there are two of them, right? So the only way for this to make sense is if the actual entries of the matrix are given simply by an inner product. So the ij entry of A is the inner product between T of Vj and Vi. So pretty easy, right, to compute now. But again, we're working under this assumption that the space is a not only a vector space, but an inner product space. So we have additional structure on V, which we didn't have before, and that's what makes things simpler. And of course, beta is orthonormal, so okay. You want to see an example of computing things like that, maybe? Now, I'm going to make use of the previous orthonormal set, so we don't have to create another one. So let's say T is a linear operator on R3. Beta is an orthonormal basis on R3. What did we call them? V1, V2, V3? Yeah, or not really. So this thing from the previous page. Just some arbitrary linear transformation on R3. And we want to find the matrix of T in that ugly basis beta, right? Okay. A11 is the inner product between T of V1 and V1, right? According to this formula above, this one here. So A11 is T of V1 inner product with V1. T of V1 is what? A plus B, 2A minus B, and 3C minus A. That's T of V1. Inner product with V1. So what do we get? 1/2 plus 0 plus 2 over 2, so 3/2.
What are A, B, and C?
For any A, B, and C in R3, that's just the definition of the linear transformation. T of A, B, C is A plus B, right? So I'm applying T to this vector, this one here. So A, B, and C are 1 over the square root of 2, 0, and 1 over the square root of 2. Yeah. So I'll probably not end up filling the entire matrix. Let's just do one more. Position 1, 2. Position 1, 2, according to that formula, is the inner product between T of V2 and V1, right? T of V2 is, so A plus B, so 1/2 times the square root of 2/3, 2A minus B, so 2 plus 1/2, 5/2 times the square root of 2/3, and 3C minus A, or 2, square root of 2/3. Inner product with V1 and that is 1 1 over 2 square root of 3 plus 0, like that's 0, plus 2 over the square root of 3. So it might look ugly, but imagine how it would have been to try to solve a system of linear equations and get to these solutions, these numbers. So it wouldn't have been easier anyways, right? So at least this is a procedure that is just computational, like basic math computations. It's not. And of course, there are 7 more entries, which I'm not going to do. Okay. The orthogonal complement of a set. So you have your inner product space V, and in there, you just take a set of vectors S. Then by S perp, you mean the set, you mean this thing here. The set of all those vectors X in V that are perpendicular to any vector in S. Think about it. Think about R3, XY plane and the Z axis, right? That Z-axis is perpendicular to anything in the XY plane, correct? So that Z-axis is the orthogonal complement of the XY plane. It's perpendicular to anything in there. Make sense? That's how it's abstractly defined in general. So you need all the vectors in your vector space perpendicular to anything. For example, let's start simple. The set containing the 0 vector only. What would be the orthogonal complement of this? 0? No. Let me write it down. X in V, right? Such that inner product between X and anything in the set should be 0. But anything in the set is just 0, because that's all I have. So all X in V with the property that the inner product between X and 0 equals 0. So which vectors in V have this property? All of them. So the orthogonal complement of the set containing 0 only is the entire space V. Okay, so the other extreme case, what would be the orthogonal complement of V itself then? Well, I would need all those vectors in V with the property that they are perpendicular to any vector in V. Is there such a thing? Well, 0 works, right? The 0 vector has this property that inner product between 0 and anything is 0. But why is it 0 only? Because that's what it will end up being.
Because if anything else belongs to V, that's non-zero, then the inner product's going to be the norm squared.
Correct. So if this thing works for every y, it will also work for y equals x, because x is also an element of V. So if y is x, that means the inner product between x and itself is 0. The only vector with a 0 norm we've seen is the 0 vector. In fact, based on this idea, can see now that the intersection between a set and its orthogonal complement can only contain the zero vector. Why is that? Well, same argument as above. If x is in both S, and I mean 0 is of course in, I would assume that 0 is in S anyways, right? Because otherwise it doesn't make sense. I just said S is a set. Usually S will be a subspace, so it automatically, that's what I had in mind. It automatically contains the zero vector. But if it's just a set, it must have the 0 in there for this picture to make sense. But if X is in both, then because it is in the orthogonal, I don't know, I wrote T, right? But it's not T. Verb. So because X is in the orthogonal complement of S, the inner product between X and anything in S is 0. In particular, the inner product between X and itself, right? If it's in both, in the intersection must be 0. So yeah, if 0 is not in S, the intersection will be empty, right? Otherwise, it must contain the zero vector. So those would be the two extreme cases again, right? The 0 set and everything. Let me just do something in between. So S is a set of vectors in R3, like those two vectors there. How would you find the orthogonal complement of S? Well, go back to the definition. I need all those vectors in R3 such that the inner product between X and anything in S is 0, right? X is, let's say, X1, X2, X3. So the inner product between X and that first vector, 1, 0, 1, has to be 0. What's the inner product between X and 1, 0, 1? Is the standard inner product again. By the way, if nothing is specified, it means it's the standard one. So X with 1, 0, 1 will be X1 plus X3, right? Has to equal 0. X inner product with a second vector in S must also be 0. So the inner product between X and 1, 2, 1. X1 plus 2X2 plus X3 has to be 0. They both need to happen at the same time, which gives me a system of linear equations that need to be solved. So in the end, S-perp will turn out to be the solution set of this system of linear equations, right? What happens here? Well, X2 has to be 0, right? If you subtract the first equation from the second, X2 is 0, and X1 is negative X3, and X3 is 3. So S-perp is the span of vectors that look like this. So the span of 1, 0. Well, Let me keep the same direction, maybe. 1, 0, 1. I wrote them horizontally initially, so I'll keep the same direction.
Yeah, negative.
Negative, sorry. Thanks. Notice one thing, S was a set, S-perp is a span is always a subspace. So even if you start with a set, the orthogonal complement will turn out to be a subspace. S could be itself a subspace or not, or just a set like here. It doesn't matter. Why do you think that's the case? Well, to be a subspace, what needed to happen? The 0 vector had to be in there. 0 is perpendicular to anything you want, so it works. It had to be closed under addition. So if you have a vector that is perpendicular to anything in S and another vector perpendicular to anything in S, will their sum be perpendicular to anything? Yes, because the sum in the first entry there splits, distributes, it's linear. And the same with a scalar multiplication. So it makes sense to be like that, it's not hard to check. Okay. So, we don't start with a set anymore. Instead of a set, we start with a subspace, W of V. W is finite dimensional, okay? And Y is in V. Y is a vector of V. The idea is that every vector of V, Y, could be split into a sum in a unique way. The sum between a vector in W and a vector in the orthogonal complement of W. Okay, so any vector could be split like this. Think about that example with R3, the z-axis and the xy, right? The orthogonal complement of the xy plane is the z-axis. Take any vector in R3, like something going in the middle like that. You can always write that as the sum between its projection, right, on the z-axis and the projection on the xy plane in a unique way, right? You just take the projection from that point onto the plane and onto the z-axis. So that's pretty much what this says. Now there exist unique vectors, u in W, z in W orthogonal, such that y equals u plus z. And more than that, you have a formula for finding u. That u will actually be called the projection of y onto W. So it's the direct expansion of what I was explaining before with that vector and projecting it into the xy plane. It's the exact same thing. Okay. So we start with W, finite dimensional subspace of an inner product space V. If it's finite dimensional and an inner product space in particular, W will have an orthonormal basis, right? Let's call that beta. And we can get inspired from this. I'm going to use the same notation, V1, V2, Vk. So there exists beta an orthonormal basis. For W. So now choose a vector in V. Well, there is no guessing here. They actually tell you what U should be. So let me define U to be that. And what is Z then? The third vector. Well, what does it need to be? It needs to be y minus u, correct? In order for that highlighted formula, this one here, to make sense. So let me just define z to be y minus u. And clearly, y is u plus z, but what else do we need to check? Well, those vectors needed to have those two properties, right? Not just two arbitrary vectors. So is it true that u is in W, first of all? U as defined here. Well, who are those VIs? Those form the basis for W, right? And U is defined as a linear combination of VIs, so a linear combination of the basis elements of W. So, of course, I'm going to get a vector in W, right? U is in W. Z, however, needed to be where? Z needed to be in W perp, so the orthogonal complement of W. All right, so what we need is that the inner product between Z and any vector V, let's say, or maybe W would be a better choice. So any vector of W should be 0, right, in order for Z to be in W perp. Okay, I'm going to take this step by step and show first that the inner product between Z and any vector in the basis of W, so any VI, will be 0. Let's see this first. Okay, what was Z? Z was defined to be y minus u, right? So y minus u, inner product with VI, which is y inner product with VI minus u inner product with VI. Okay. I don't know anything about y, so I'm going to let it be like this. I'll look into the second one. I know something about u. It's that formula over here. It's a linear combination. It's in the first entry of the inner product, so it's going to distribute, right? So it's going to be the sum, I equals 1 to k. Y, Vi were the coefficients. Well, I cannot use the same I, right? You say j. Y, V, j. And then that will be Vj inner product with this Vi. Make sense what I did? I took this entire sum, replaced it in here, and then distributed according to the sum and those scalars which I pulled out. Okay, so it turns into this. Now, Vi with Vj, that set beta was orthonormal. So in particular, it's orthogonal. So Vi with Vj inner product is 0 unless j equals I. So I'm just going to retain from this the case when j equals I. Vi inner product is the norm of Vi squared, but again, beta was orthonormal, so they all have norm 1. So this is 1. So you end up with 0, right? So Z is orthogonal onto any vector in the basis beta. That's not enough. I want it to be orthogonal onto anything in W, but it will be automatically implied by this. Because a vector W in W is a linear combination of the vectors in a basis. It's not up to k, it's up to n is up to k. Right, so W is a linear combination of the elements of the basis beta. I'm going to pull this out. It's linear in the second, except that the scalars go out in conjugate form. It doesn't matter though, because we've seen that the inner product between Z and any VI is 0. Correct? So in conclusion, Z is orthogonal, is in W perp. Okay, so what have we done so far? We proved that any vector can be written as U plus Z, U in W, Z in W perp. There is one thing that we haven't proved though. And it's that word there, unique, right? There is no other way to do that. And in general, to prove uniqueness, you just assume that there is another way. So let's just say so Y is U plus Z, where U is in W, Z is in W perp. And let's just assume that there is another way to do the same thing. So Y equals U prime plus Z prime. U prime in W still, and Z prime in W perp. The goal is to show that U equals U prime and that Z equals Z prime. Just go ahead and subtract them. Not only subtract them, I'll move them around like this, right? Because when you subtract them, you get U minus U prime plus Z minus Z prime equals 0. So I write it as U minus U prime equals Z prime minus Z by subtraction. Why do I want to write them like this? U and U prime were in W, right? W was a subspace, so the difference is still in W. Z and Z prime were in W perp. W perp is always a subspace, as we noticed, right? So the difference is also in W perp. So now we have this element, U minus U prime, let's say, that belongs to both W and W perp, and that can only happen if it is 0. Subspace W, so it must contain 0 this time. Hence we have uniqueness. Okay? And the formula that we have here, of course, is part of the proof, so that's how it works. So I'll stop here. We'll continue next time with how to apply this to a specific situation. So no decision, right, on when to have the makeup sessions. So this time I will come up with some possible times. Yeah, but Monday you can do it, but Kevin, no, not really. Okay, I'll make a list of times and you reply and see what happens. Maybe one of those voting sites where you just, we'll see. Just stop here.